Welcome to 1007 ICT, 1807 ICT, 7611 ICT, Computer Systems and Networks. This is Lecture 2A, Data Representation. So in this lecture, we're going to talk about how is data stored in the machine. In the previous lecture, we talked about the basic components of computer systems, just a little bit of background, and then how computer hardware has evolved over time and where it's going. A lot of really interesting topics there. So in this lecture, the content that we're going to look at is what is computer data, how do we store information in the computer so that we can use it effectively, we can process it in certain ways, we can do maths with it, we can make pictures from it, all that kind of stuff. And you'll find that there's a really simple underlying mechanism that we use, the binary number system, which we use in clever and creative ways to do all these complicated things. So what we're going to look at in particular is representing binary integers. What are those things and how do we represent them? How do we calculate their values and so on? We'll look at converting from binary to decimal. So as people, we work with decimal numbers, base 10. This is a different base 2, or binary numbers. So we're going to have to convert between our base 10 numbers and base 2 numbers. So we'll see how to do that. We'll look at the powers of numbers in different bases. We'll see a table talking about those differences and the similarities between the different bases. We'll look at integer word sizes. So an integer is a whole number. And we'll look at when we get certain collections of these binary number bits together, we can generate certain kinds of numbers. So we'll talk about how we generate those and what it means when we talk about a 32-bit number, for example. We look at converting from decimal to binary. That's also useful for us. We're working in decimal. We want to convert a decimal number to binary. We need to know how to do that. Hexadecimal and octal representation. So not only are we going to talk about binary numbers, base 2, we're also going to talk about hexadecimal, which is base 16, and octal, which is base 8. Now you may notice already, 10, base 10, is not a power of 2. 2, 8, 16, they're all powers of 2. Yeah, so we'll see some relationship between those. And you'll see that theme going through a lot of the stuff that we talk about. Okay, so the learning objectives. We will gain an understanding of what is computer data, and then we learn how to do each of these things. So we're going to learn some process. So there's going to be some practical applications of this, and we will apply this stuff in the workshops, and you'll do lots and lots of these. Initially, this may seem quite challenging. That's perfectly fine. You will do enough of this that in a couple of weeks you'll probably go, oh, actually that's not too bad now that I've done it a few times. And that's typically the experience that I hear from people where they start off saying, actually this seems really complicated, do it a few times, oh actually now I'm looking at it and I'm thinking that I thought that used to be really difficult, but now it's actually just second nature. Now I can do more difficult things on top of that. That's how we build this kind of knowledge. So looking at computer data. So data is basically any type of information that can be stored in a computer memory and processed in some way. All kinds of information can be stored as long as you can somehow represent it as a series of zeros and ones. And it turns out that actually we can represent anything as a series of zeros and ones. If you want to represent numbers, you can do that with a series of zeros and ones. We'll see that particularly in this lecture. If you want to represent animals, well, if you have a lookup table and you say dog is number 1, cat is number 2, a frog is number 3. Does that make sense? And you can turn those numbers 1, 2, and 3 into binary values. Then you can store frogs and dogs and cats and all those kinds of things, as long as you have a table that tells you which one's which. Can you see you can store anything you like if you follow that approach? Okay. So some examples of different data types. And by the way, just when we talk about these ones and zeros, there's an electrical equivalent to this. Right? So we're talking about ones and zeros. 1 is on, 0 is off. In terms of power, 0 means no power, 1 means there is power. Or a difference in power you could also use. Does that make sense? Okay. So we can represent electrical signals as zeros and ones. How does a computer work? Electrical signals. Yep. So we can map those electrical signals to our zeros and ones somehow. So some examples of different data types. So just looking at some examples here, the numbers in the red there, so the zeros and the ones. We can represent text or characters. So 0, 1, 0, 0, 0, 0, 0, 1 apparently is the letter capital A. Apparently. When we learn more about ASCII characters, you will probably see, actually yes, that is the lookup table representation of the character capital A. Capital B will also be a series of zeros and ones, and it'll be a different series of zeros and ones. Yeah? From what I understand about the ASCII table, it's most likely 0, 1, 0, 0, 0, 0, 1, 0. Okay? And you would be able to do that calculation in your head as well once you understand about the ASCII table and you see how that actually works. Does that make sense? Okay, so one thing I will say about those digits in red, the zeros and ones, there are 8 of them. We tend to work in groups of 8. Okay, so you'll see that as a common theme. Right, so we tend to work in groups of 8, and we can glue them together. We get 8, 16, 24, 32. Yeah, we have 8-bit computers, 16-bit computers, 32-bit computers. What was the next one? 64-bit computers. Potentially the next one will be 128-bit computers. Right, you can see how that kind of works. We can represent lots of different kinds of numbers. Now, the number 3 might be 0, 0, 0, 0, 0, 0, 1, 1. And I'll show you why that is later on in this lecture. Right, so you'll see an example of how you can compute that that is the case. The thing is that if you're working with numbers, that series of zeros and ones must always equal the same thing. It must always be 3. You can't have it be 5 some later time. It has to always be the same thing. Data processing instructions. So inside the computer, you can tell it to do things. You can tell it to add numbers, subtract numbers, multiply. Apparently, on some machine somewhere, the instruction add two numbers is 000110001. Okay? I'll take that on faith, right? Probably is. But again, it's just an identifier for that particular instruction. Another instruction will have a different identifier, a series of 8 ones and zeros. The last one's probably the easiest one to think about, audio and images. There's 8 ones. If you're thinking about images, let's take images as the sample here. If you have all ones, what do you think that means? Everything is on. What color do you think that is? It's white. What about if it's all zeros, everything is off? It would be black. That's a really nice natural mapping. And if it's half zeros and half ones, it would probably be some kind of gray in the middle between those two. Yeah? Okay, so that's a basic understanding of what we mean when we're saying we're having these ones and zeros to represent particular values or things inside the system. We're not really storing ones and zeros, they're electrical signals, but we're using an abstraction. We're looking at it from a slightly different viewpoint. So, since each of these is stored as bits, how those bits, and each one of these zeros and ones is a bit, it can be on or off, how those bits are determined depends on what type of data the computer expects or thinks it's working with. So if you tell the computer this is going to be a number, it will interpret those ones and zeros as a number. It won't try and treat it as an image pixel. Does that make sense? It won't try and think of it as an instruction. It'll say, okay, this is a number. These are the rule for numbers, right? So this thing means, in that case, 3. If you tried to take it as an instruction, it would be a completely different thing. It would be the instruction of 00000011, whatever instruction that is. So it depends on what the computer thinks it is, and you will tell it in some way. Now, when you write a program, you may have already done something like this or seen that. You will say typically something like variable declaration int x. Yep, something like that, or char y, or float z, or something like that. That's telling the computer this thing is going to be that type of value. An int is an integer, it's a whole number. A float is a fractional number with a decimal point. Does that make sense? So somewhere the machine understands what it's working with. Okay. So that's just a little bit of background. Now we're going to go through how it's actually representing those numbers. So if you look at this page, there's a summation symbol in the middle there. That's a little bit detailed. I'm going to go through that in a slightly different way. But an integer is a whole number, not a real number, so not something with a decimal point. We're going to keep it simple. We'll talk about decimal numbers later. Integers can be represented in binary form by writing them in base 2 instead of our common base 10 notation. So before we go on here, I'm just going to go and talk about base 10 and its relationship to base 2 and so on. So we are very familiar with base 10. This is the number system that we use. And it has digits 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. How many digits are there? 10. Okay, base 10, there are 10 digits. Okay? This is the one we use all the time, right? What I'm going to show you is actually this binary number system, hexadecimal, octal, all these number systems work exactly the same way. So you already know how to do this. There's nothing new here. It's just a little bit different to what you're used to. Okay, so just keep that in mind because you already know how to do this stuff. So when we're working with base 10, What we do is we have a ones column, a tens column, a hundreds column. What's the next column? The thousands column. And we just do this automatically. You've learnt this through schooling, right? It's just ingrained for us at the moment. So what that actually means is 10 to the 0 is 1. So this is the 10 to the 0 column. Yeah? 10 to the 1 is 10. So this is the 10 to the 1 column. 10 to the 2 is 10 squared, which is 100. This is the 10 to the 2 column. This is the 10 to the 3 column. So 10 to the 3 is 1,000. And so in base 10, this is really easy and convenient for us. Every time you go to the next column, just add a 0 on the end. Yeah? That's actually really easy. It's convenient. Other bases work exactly the same way, but they have a different number here. Instead of 10, they will have a number 2 or 8 or 16 or something like that. So if I'm working with a number, let's have a look at a number. If I'm counting, okay, so 1. Actually, let me just put it under the right thing here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I've run out of digits. Is that correct? I have no more digits left. They're all the digits that are available to me except for the 0. Yeah? So what happens is now I've got up to 9 ones. The next value will be 1, 10, and 0 ones, which is 10. If you add those columns together. So there is 1 lot of 10 and 0 lots of 1. That's equal to 10. Then we have the next number will be 1, 10 plus 1, 1. Yep. To see this a little clearly, or more clearly, you can see that this is 0 tens plus 1, 1, which is 1. This is 0 tens plus a 2, which is 2. You see how that works? So the next number down here will be 1, 10, and 2 ones, which is 12. Then you go all the way down to here, and you'll get eventually to 9 tens and 9 ones, so 99. We have run out of digits, and now we want 1 in the hundreds column, nothing in the tens, and nothing in the ones. That's 100. 100, no tens, and 1, 1 is 101. You're doing this all the time, right? So this is not new. This is maybe a slightly different way of looking at it. But this way of looking at it is going to be very helpful when we're looking at the other bases. This is the mechanism that we're using. So let's go on to base 8. So you'll see base 8. Base 8 is also called octal. So in base 8, you would expect that you have 1, 2, 3, 4, 5, 6, and 7, and then a 0. 1 less than the base number. So in base 8, you also have a ones column because 8 to the 0 is 1. Anything to the 0 is 1. 8 to the 1 is 8. 8 to the 2, 8 squared is 64. Do you want to be working in this base a lot? It's probably not. It's probably difficult for us to work with powers of 8. Yeah? 64. What's the next one? 8 times 8 times 8, right? So 8 times 64 is some number. Yes? But let's look at how it works, right? So 1, 2, 3, 4, 5, 6, 7, exactly the same. I've run out of digits. So the next number will be 8. So 8 is 1, 8, and 0 ones. 1, 8, and 1, 1 is 9. 1, 8, and 2 ones is 10. Eventually, you will get to 7, 7. And 7, 7 will be 7 times 8, yeah, which is 56. Plus 7 is 63. The last one until you need the next column, which will be 64, with no 8s and no 1s. That's the 64. Can you see how it works? Do you think you'll need a little bit of practice with this? Probably, yeah, that's fine. Just try some of these out. But what I'm trying to get to is you already know this. This is not new. This is just a slightly different way of looking at what you're already doing. So in some sense, this will take a little bit of time. It won't take a very long time to get to grips with it. So we do use base 8. Okay, we don't use it that often, but you should be aware of it. There's also base 16, which we'll talk about later. But we also mostly use base 2. Now base 2 in some ways is really easy. You have these numbers. That's 2. It's easy, right? It actually makes it a bit more complicated too, because you have less differentiation between the digits. So, in base 2, well, what's our first column? 1, right? 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. 2 to the 4 is 16. Can you see a pattern here? 1, 2, 4, 8, 16, 32, 64, 128. We usually stop at 128 because that's 8 bits worth of stuff. Yep. So once you memorize or work with those numbers a lot, they'll become second nature. They'll become very easy. So how do we count this stuff? Well, let's have a look. We start with 0 and 1. And this time I'm just going to start with 0 because there's not very many digits to play with. So 0 is 0. This is 1. It's pretty straightforward. I have run out of digits. There's no more digits. There's very few, right? So what's the next number? 2. And it'll be 1, 2, and no zeros. 1, 2, and 1. 1 is 3. So this is 2, this is 3. And again, I've run out of digits. I'm going to run out of digits really quickly. So I need a 4, no 2s and no 1s, and that's a 4. A 4, no 2s but 1, 1 is 5. A 4, 1, 2, and no 1s is 6. A 4, 2, and a 1 is 7. And again, I've run out of digits. Okay? And so what you can see, there's a couple of things going on here, is this the same mechanism that we've seen before? Exactly the same. So you can already do this. Next thing I'll show you is there's some patterns. So this 0 and 1 just keeps repeating. In the 1s column, you'll just get an alternating 0 and 1. Yep? If I fill in some leading zeros here, in the 2s column you'll get 2 zeros and 2 1s. And then 2 zeros and 2 1s. In the 4s column, if I put in some leading zeros, you get 4 zeros and 4 1s. What do you think in the 8s column? 8 zeros, 8 1s. There are some patterns here, and you may be able to use those effectively a little bit later on once we start working with this stuff. Just be aware that there are patterns, and they can be handy, or they can be useful to you later on. Okay, so what we did, right, we looked at how the number system works. And I did that deliberately before talking about this summation symbol, because it's a bit mathy, right? There's like, if you're not familiar with that symbol, it's the summation symbol, which just you use to add up a number of values in a row, in a sequence, right? And so what that value or that summation symbol there is saying, or that formula, it's saying, look, for any base and any set of digits, you can calculate the value. That's really what it's saying. It's a shorthand for that. So I'll show you a couple of things to do with that. It's what we've just been doing, by the way. Just we've been doing it a slightly different way. So this is a summation from I is 0 to n, and I is attached to this d and this b. So this is d sub I, this is the digit I, and this is the base to the power of I. So b is the base. I is the thing we're going through, the counter, and d is the digit. So let me give you an example of how this works, and I'll show you the easy example first. I'll take a number like 147 base 10, and you'll notice I'm putting a little 10 underneath it, just to indicate that this is base 10. We are now working in multiple different bases, so it's important to put that number there so that you can see which one you're actually talking about. Okay, so 147. Well, this is when I is 0. So this is the 10 to the 0 column. This is the 10 to the 1 column. This is the 10 to the 2 column. We agree with that based on what we said before? Okay, so when I is 0, we are looking at digit 0, that's the 7. Okay, so digit 0 is 7. 7. And it's times, what's b? We are in base 10. 10 to the, and what column are we in? 10 to the 0. 7 times 10 to the 0 is 7 times, what's 10 to the 0? 1. 7 times 1 is 7. Okay. But it's a sum, right? This is the summation. So then that's plus I equals 1. So what number are we going up to? We start at 0, we go through 1, and we end at 2. That's how many digits this number has. So when I is 1, this is 4 times 10 to the 1, which is 4 times 10 to the 1 is 10, which is 40. Plus, when I is 2, this is 1 times 10 to the 2, which is 1 times 100, which is 100. Now if I add them up, 100 plus 40 plus 7 is 147. Now this is in base 10 already, so it's easy. Does that make sense? Right? We can do this with other bases too and get a value out of it though. Okay, but you can see the mechanism. That's what that summation symbol is showing. So let's do this with another value, and I'm just going to pick a base 2 number. So 1, 1, 0, 1, base 2. And you'll notice that I need to write the 2 here because this could be a base 10 number. It could be 1101 if I don't write that base 2 on the bottom, we would get confused. So in this case, which columns do I have? This is 2 to the 0, this is 2 to the 1, this is 2 to the 2, and this is 2 to the 3. We agree with that? So when we do this summation, we're going to go from 0, 1, 2, 3, and we're going to add them up. Let's just look at the column values though. This is the column value 1, 2, 4, 8. In general, we will work with that 1, 2, 4, 8. It's easier for us to work with, but we need to know that it's 2 to the 0 because their formula depends on it. Right? When you're counting, you need to know which column you're looking at. And the column number is the 0, the 1, the 2, the 3. Okay? So, when I is 0, what we have is this column. 1 times 2 to the 0 is 1 times 1, which is 1. Okay? Plus, when I is 1, it's 0, it's this one, times 2 to the 1 is, well, 0 times anything is going to be 0, but what's 2 to the 1? 2? 2 to the 1 is the number itself, right? So 2. So this is 0 times 2 is 0. Plus, I is 2. That's this column. 1. 1 times 2 to the 2 is 1 times 4 is 4. Plus, I is 3. 1, that's this one, times 2 to the 3 is 1 times 2 to the 3 is 8, plus 8. So 1 plus 0 plus 4 plus 8 is 13. Okay, so does it work for different bases as well? Yep. Okay, so let me just recenter this page. Here we go. And so another way, this is the long way, right? This is a long way to do it. What you can do is you can just say, okay, well look, there's a 1 in the 1s column here. Add 1. There's nothing here, don't add anything. There's a 1 in the 4s column, so I had 1 plus 4 is 5. There's a 1 in this column, plus 8 is 13. Can you do this very quickly? You don't have to do all these steps, right? These steps down here, you don't have to do all those. You can just do it by adding up the column values. So we can make this a lot more efficient. We're showing you now how the underlying process works, what the theory is underneath this, but you can do this in practice much quicker. Okay, so we just went through this slide, and I gave you some examples. We also went through this slide. By going through those examples, I've shown you a couple of different ways, to compute this information. We'll do a lot more of this, by the way, so you'll get a lot more practice at seeing how this works. But can you see that actually it's pretty straightforward, or pretty simple in terms of the things that you're doing? The initial challenge will be that you're working in a different base. It looks different, right? There's only 1s and 0s. That makes it a little bit more complicated to think about at the start. All right, but you will get used to that fairly quickly, actually. Okay, so some examples down the bottom. Binary to decimal conversion. You'll see that it says 0.00000011 is 2 plus 1 is 3. Remember at the start of the first slide we said the number 3 looks like this, and I said I'll prove to you that that's actually the number. Well, let me do that. And so what we said was I had this number 0.00000011, and we said that this was 3. Can we confirm that now, or can we say that's actually not accurate? Well, let's have a look. This is the 1s column, the 2s column. 2 plus 1 is 3. This is the 4s column, nothing. 8, 16, 32, 64, 128. There are 8 bits here. We normally work in 8 bits, so typically you'll count from 1, 2, 4, 8, 16, 32, 64, 128. And you just add up the columns. If there was a 1 here, what would the number be? 3 plus 32 is 35. Okay, so we'll do another one, just very quickly. So we have a number like this, slightly bigger one. Looking at that number, what number is this? 1, 2, 4, 8, 16, 32, 64, 128. It's 36. Okay, so you get used to this fairly quickly, I think, right? But you do, if you're working this stuff out, I recommend that you write those numbers above the columns. Trying to do this in your head typically is not that easy, especially if you have more than a couple of 1s in that sequence, right? It's going to become more difficult. Okay, so we have confirmed what we said at the start. That number is 3, and you can see some of the other numbers. I invite you to practice some of these. Just try some out, write down some ones and zeros, and see what you get. Right? It's an easy thing, an easy process to practice in that way. We're looking at powers in different bases, and so you'll see here we have decimal. We talked about base 10. Base 10 is easy for us. We just add a 0 every time we get a new power. 1, 10, 100, 1,000, 10,000, and so on. Binary and hexadecimal and octal are a little bit different. They're still the same mechanism, but the numbers look very different. So if you look at binary in the middle table, 1, 2, 4, 8, 16, 32, 64, 128, then 256, 512, 1024, 2048, 4096, 8192, 16384, like there's a whole bunch of those. I don't expect that you will memorize those. You can compute them. Does that make sense too? You can just double each time. So you can start, it takes a little bit of time, but you can generate those numbers. But you do need to be very familiar with the first 8, right? Because we use those all the time. Looking at hexadecimal and octal. So hexadecimal is base 16. Now we use base 16 because it's a power of 2, and you'll see there's some overlap. So look at hexadecimal, they're base 16 on the right, the top part of the table. 16 to the 0 is 1. Okay, there's an overlap. 16 to the 1 is 16. Is that in the binary table? Yes, 2 to the 4 is 16. So there's an overlap between these two number systems. 16 to the 2 is 256. Is 256 in the binary table? Yep. What about 4096? Well, it's not in this table, but yes, it is in there. So we can actually use hexadecimal as a shorthand for binary. What that's really saying, this table, is that when I have 4 bits, so 2 to the 4 is 16, when I have 4 bits, I can use that to represent, or I can use one hexadecimal digit to represent 4 bits. Remember one of the problems we just had with those binary numbers? When you see a bunch of 1s and 0s, can you tell what number that is? No. When I'm saying 0011, 00111, can you remember that sequence of digits? It's very difficult, right? So instead of having 4 of those 1s and 0s, if we can shorten that into a single digit, like 1, 2, 3, 4, or D or something like that, it makes it much easier for us to work with. It's still difficult, right? But it just simplifies things. We'll show you that in a minute too. There's another table coming up. So that's one reason why I use hexadecimal. It just seems like a weird base 16 to work in, but that's why. Octal, base 8. Base 8, is there a relationship between the base 8 and the binary? Yes. 8 is in both, 64 is in both, 128 or 512 is in both, I should say. And so, again, hexadecimal uses 4 bits for 1 digit. Octal, where does it wrap around? 2 to the 3 is 8. So 1 octal digit represents 3 binary bits. Again, I'll show you a table a little bit later on that sort of illustrates that. But just keep that in mind. These are not random bases. They seem random at this point, but they're not. There's a reason why we chose them. Okay, so those are the bases. Now we look at the bits and the values. If we have n bits, we can represent 2 to the n different values with those n bits. So I'm just going to show you a table. I'll just draw this table up, and this will hopefully clarify this, I think, fairly well. So if I have a number of bits, and then I have some possible values, and then I have the number of values. So let's start with a number of bits. I have 1 bit. It can be on or off. So how many possible values do I have? Right? Well, I have 2 values total, and the values can be 0 or 1. Does that make sense? Okay. So that's pretty easy. What about when I have 2 bits? Well, I can have a 0 and a 0, a 0 and a 1, a 1 and a 0, and a 1 and a 1. Those are my possible values for this, right? 2 bits. How many values are there? 4. Okay, good. When I have 3 bits, I can have 0, 0, 0, 0, 0, 1, 0, 1, 0. And you'll notice what I'm doing here. I'm doing this in a particular order, and actually I'm counting. Yep, I start with 0, 1, 2, 3, 4, 5, 6, and 7. And there are 8 of them. So how many possible values are there? 8. Can you see a relationship in this column? What's the next one? If I have 4 bits, what's this going to be? There will be 16 possible values. Yeah, and they'll go. I'm not going to write them all out. Obviously, I don't have space all the time, but you can see how that would work, and you can generate this yourself. So maybe you want to do that at the start and just verify for yourself how this works. And one of the things you'll see here is that this is 2 to the 1. Where does this 1 come from? It's the number of bits. This is 2 to the 2. Where does the 2 come from? Number of bits. This is 2 to the 3 because we're using 3 bits. 2 to the 4. So the number of values that you can represent is related to the number of bits that you have. If you have 5 bits, you can represent 2 to the 5 things. Yep. Okay, so that's important. That's something that will come up in lots of different ways throughout the course. So that's what this table is really saying to you. Right? How many bits you have determines what you can represent, and it also determines the range. So if you look at the range, the number of bits, if there's 1, the values are 2, and the range is 0 to 1. 1 less than 2, right? What about if you have 8 bits? You can represent 256 things, because 2 to the 8 is 256, but the range is only 0 through to 255. In general, if you have n bits, you can represent 2 to the n things, but the range will be 0 to 2 to the n minus 1, because you have a 0. The 0 counts as a place. In normal maths, we don't start counting from 0. We start counting from 1, right? So just keep that in mind. There's a 0 at the start that changes the dynamic of it. Okay, so we have a decimal to binary conversion next. We'll be doing a lot of this. Just want to say about this slide, I want you to read it, I want you to have a think about it. It's very wordy. It's an algorithm or a process for doing something. It's written in a particular way so that it's not ambiguous. If you follow it, you'll get the right outcome. Problem with that is, for us, when we're beginning to learn this, it's very difficult to understand. Right? So I'm going to show you an example. There's an example on this page you can step through yourself. I'm just going to show you a visual example. Explains exactly what's going on here. It'll be much easier to interpret that than probably starting from reading this thing. But please do read that and see how it matches. Okay, so example I'm going to show you is I'm just going to do a small number like 49. Okay, so 49 base 10. I want to turn this into binary. It's actually pretty easy in some ways. There's a little bit of calculation involved, but the process is this. 49, okay, the biggest number that can be inside 49 is 49. Would you agree? If you have a 50, is it going to fit inside the 49? No. So what we have to do is we look at the powers of 2. We start with 1. Does 1 fit inside 49? Yes, it still fits. So it's potentially part of the 49. 2. Yes. 4. I'm just going through the powers of 2. 8. Still fits. 16. Still fits. 32. Still fits. 64. No way. That does not fit. So I can stop there. So I now know which of these columns are potentially part of my answer. And all I did was I just counted 1, 2, 4, 8, and I stopped when I got too big. So is there a 32 in 49? I'm going to start from the left, and the answer is yes, there's 1. There cannot be more than 1. It can only be 1. So I subtract 32 from 49 and make my number smaller, and what's the answer? 17. Now I'll go to the next column. Is there a 16 inside 17? Yes, 1, exactly 1. I subtract 16, and now I have a 1 here. Is there an 8 inside 1? But this is what's left over. This is what I'm looking at. Is there an 8 inside 1? No. Is there a 4 inside 1? A 2? No. A 1? Yes. Minus 1, and I get 0. I need to reach 0 in my calculation here, and now I have the answer. You can do a sanity check here, right? You can look at it and go, okay, this is a 1 plus a 16 is 17 plus a 32 is 49. Now, typically when I do the sanity check, I would start from the big end first. It's easier to add those numbers up. 32 plus 16 is 48. You'll get used to those numbers. That becomes easier. Plus 1 is 49. That's an easier calculation to do than 1 plus 16 plus 32. Okay. So we can go both ways on this thing, and you can verify your answer. You can check, did I get it right? If you didn't, maybe you made a mistake in the subtraction here, or maybe something went wrong here. Yep. Okay. Now what we look at is not just one way to do this. I'll show you the next one. Here is an alternative way to do this. So this is decimal to binary still. This one, usually there's more than one way to solve a particular problem. So this time we have a slightly different algorithm or a different process. I find this one more difficult for me personally. Some people find this easier. So if you're someone who finds this easier, use this one. It doesn't matter, right? And you'll find the same thing for other processes that we have. If there is a process that you find easier to do that still works, use that one. No problem. Yep. Okay, so this one, the way it works is you recursively divide the decimal number by 2, noting the remainder each time. And the remainder will either be a 0 or a 1. If you divide something by 2, either it divides evenly, there's no remainder, or there's a remainder of 1. Yes? Let's have a look at that. Okay, so I'm going to show you, again, you can read the instructions, you can see the example and work through it, but I'll just show you a visual way to look at it, and hopefully that makes it a bit easier to work out what's going on. So with this algorithm, I'm going to start with, again, a small number, 79 base 10. So 79. 79, actually I'll start on this side. 79 divided by 2 is 39 remainder 1. Is that right? What do you think? 39 times 2 is 78, and there's 1 left over. So the answer is 39 remainder 1. Now what I have left is this 39. So 39 divided by 2 is 19. 2 19s is 38. There's a remainder of 1. There's 1 unit left over that I can't account for. 19 divided by 2 is 9 remainder 1. Okay, so far it's looking a bit, how are we going to finish, right? You'll see. 9 remainder 2 is 4 remainder 1. So now we're out of this 9s sequence. 4 divided by 2 is 2 remainder 0. There's nothing left if I divide 4 by 2. 2 divided by 2 is 1, goes once, and there's nothing left over. Is that correct? 1 divided by 2 is 0. It does not divide, and the remainder is 1. If I try and divide 1 by 2, it does not divide, and what am I left with? 1. Okay, it doesn't work. So, have I finished? Well, I've got a 0 here. There's nothing left. I can stop. So this algorithm, what it says is that if you take these values and you do this, you'll see that you ended up with a bunch of 1s and 0s. Is that correct? And you have here a 1, a 0, a 0, a 1, a 1, a 1, and a 1. So a bunch of 1s and 0s in a sequence. This is the order. This is the 1s column, the 2s column, the 4, the 8, 16, 32, and 64. 64 plus 8 is 72, plus 4 is 76, plus 2 is 78, plus 1 is 79. This process also works. If this is easier for you to work with, use this one. If the other one is easy for you to work with, it's definitely easy for me to work with the other one. If it's easy for you, pick whichever one you want. They both have the same outcome. Okay, so we've now seen how we can convert decimal to binary, and before I showed you how to get binary to decimal, right? We've seen both ways now. Hexadecimal. So hexadecimal is interesting in a lot of ways. It's base 16. Base 16 is a difficult number for us to work with. We don't really work well with 16. We don't have 16 fingers, right? So we have 10 fingers, right? Yeah, on hands, so that makes base 10 a little bit easier. We can just count. 16 is more difficult in lots of different reasons, but hexadecimal and binary numbers are very closely related. We saw that in those tables. 16 is a power of 2. That means we can do some nice things with this. In terms of converting, it's really straightforward. There's a table there. I'm going to show you this table, but I'm going to write it out, and I'll show you a couple of things about relating this table to different bases. So we'll start here with 1, 2, 4, and 8. We have 4 bits. Let's only need 4 bits. Okay, and in those 4 bits, we're going to start with all zeros. This is the number 0. This is the number 1. This is the number 2. Number 3. So I'm going to write all these out, and we'll get a look at what it looks like. This is the number 4. Can you see I'm counting? Yeah, I'm just filling in the columns by adding 1 in the and just making it flow through. So this is a 5. 4 and a 1 is a 5. This is a 6. A 4 and a 2 is a 6. This is a 7. A 4 and a 2 and a 1. This is an 8. Just an 8. This is a 9. This is a 10. This is an 11. You'll notice on the right here I'm counting, but I've run out of digits, right, in base 10. So we'll have to deal with that. So 1, 1, 0, 0 is an 8 plus a 4, which is 12. 1, 1, 0, 1 is an 8 plus a 4 and a 1, which is 13. 1, 1, 1, 0 is 14. And 1, 1, 1, 1 is the biggest value you can have in 4 bits, which is 15. The numbers range from 0 to 15. How many digits, how many numbers are there? 16. How many digits can we actually use? 0 to 9. That's how many digits you've got on your keyboard. That means that 10, 11, 12, 13, 14, 15, they don't have their own digits. We're going to have to make up some digits. So what we do is we make 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. Which is why when you look at hexadecimal numbers, you'll see A to F in those digit columns. That's different from what we normally do, right? But they're just symbols. So A is equal to 10 if you're working in hexadecimal. A couple of interesting things about this particular section. So this is 4 bits. So all of this stuff is base 16. Yep. 3 bits goes down to here. This is octal, or base 8. When you only have 3 bits, you can count from 0 to 7. Does that make sense? That's the octal values. So you can write out this table, and I recommend that when you're practicing this, just write this table out and review it. Just look at it, right, backwards and forwards. When you're in an exam, rather than working out this stuff all the time, at the start when you can first write this table out. You probably only need up to 15, and you can just look it up. You will make a lot less mistakes that way. Right, so use this kind of technique to help you, at least initially, get used to this stuff. Okay, so what we found was that with base 16, if I have this number, 11010011, big number, yep? If I say this to you, 11010011, are you going to remember all those digits? Not very easily. So what I can do, this is the 1, 2, 4, 8, 16, 32, 64, 128. I can convert this to decimal. We know how to do this now, right? It's 128 plus 64 plus 16 plus 2 plus 1. Whatever that value is, we could do that. What we can also do is something a little bit more clever. We can compress this number. So we can say, okay, look, we chop it up into 2 groups of 4 bits. So that's one group, and this is another group. If I have 4 bits, I can use those 4 bits to represent a hexadecimal number. So this number is 1 plus 2 is 3. And this number is an 8 plus a 4 is 12 plus a 1 is 13. Based on our previous table, 13 was D. D3. If I say to you D3, is that going to be easy for you to remember or work with? Yeah, it's much simpler than 8 ones and zeros. So you can see at least one reason why people use hexadecimal. It's to compress these numbers, to make them more manageable. Okay, so that's just a little bit about hexadecimal and also octal, and I wanted to show you the relationship. Also, when you're working with these hexadecimal numbers, if you don't have any letters in there, you can't tell that it's that it's a hexadecimal number, right? Just by looking at it. So when you see a hexadecimal number, usually they put the value 0 and then an X in front of it, so that you can tell that this is a hexadecimal number, right? So that's a notation inside the computer. And you can use capitals or lowercase letters, by the way. It doesn't matter which one you use. I prefer uppercase letters or capitals because it's just easier to identify those. Octal. I already talked about octal. It's in that table. 3 bits. Counts from 0 to 7. Okay, so if you're going to work with these, please do the whole table. I think it's much, much more useful. And you can do that conversion. So in summary, we have looked at representing binary integers. We've looked at converting from binary to decimal, the other way around, decimal to binary, and we had hexadecimal and octal representations. And next time we will continue, we'll look at binary addition and representing negative numbers. That's something that's going to be quite challenging. 1's complement and 2's complement is the way that we're going to do that. And then we'll look at representing character data, images, and audio. And that's the end of this section.